we will do more examples of triple integrals as we go. There's plenty to do as we learn more content. Let's go on to 15.6. And I want to narrow down a bit what we're going to do on this section. This is applications, triple integrals. Specifically, this is basically moments about an axis and mass. And so this, you would have seen some of this in Calc 2, talking about center of mass and moment, that kind of stuff. So the basic idea for this is if you have a system with, this is like the point mass concept. So M1, M2, and then it's distance from like the balance point, right? You do the product times M, product times M2, and that gives you the moment. So we're not going to do that a lot. What I want you to, well, at all, what we're going to focus on is calculating mass with a varying density. So that's the idea. So what I want you to look at are these problems in that section. So in 15.6, look at 29 through 34. And that is calculating mass with a varying density. So the idea is then, so what if we want, we're looking for this. So this example I have on the left here with a sphere. Suppose you have a volume, but in a solid, but inside that solid you have a density that's varying. So this example might say the density, and they use a delta. The density delta is directly proportional to the distance from the xy plane. So here's the xy plane, and the k times z would be that distance. So the density here is different than the density up here. So that's a varying density. So that's what would be in your function down here, would be a varying density. So when you do that calculation, you're adding up each tiny little point like this as you add it up, and it's going to have a different mass. So it's like you're adding up these little values and you're taking that sum over the solid. So that's the idea that I want you to do. There's a lot more in there, but that's what I want you to focus on. That's what I will ask you, or may ask you. So let's look at, so this would be, so mass, this is the basic setup. Mass is equal to the triple integral, so that's volume, times the density function. So recall that mass is volume times density. And so I did a little divided here. So if the density goes up, for it to be a constant volume, the mass has to go down. So it'd be a smaller thing, right? Or vice versa. If the density goes up, then the mass has to go down for it to be the constant volume. So mass is volume times the density. Okay, so now let's look at an example. So a solid Q is bounded by a cone, z equals the square root of x squared plus y squared, and the plane, so basically just cuts it off, z equals 2. Now here's the statement for the density function. The density, delta xyz, so it's a density at a particular point, is directly proportional to the square of the distance from the origin to the point. We'll get to that in a second. So let's first draw in our picture. So we have a cone that's, say, here. So you have some cone like this, like that. Okay, and it's cut off right at z equals 2. It's cut off here, so here's your cone. The lower function is z equal to the square root of x squared plus y squared. All right, so then we have, oh, wait a second. I was looking at the wrong one. I think this is still the same. Okay, true. All right, so then I'm going to keep going. So our mass, m, is the triple integral over the solid, which we drew over there, of delta x, y, z dv. So the distance from the origin is basically that distance formula. So you take any point, distance between 2 points is the sum of the square root of the squares, or the difference of the squares of the components. But one of the components is at the origin, or one of the points is the origin. So the delta, till delta x, y, z, then is equal to the square of the distance from the origin. So the distance is the distance formula, so it's directly proportional. And then when you square the square root, you could just get x squared plus y squared plus z squared. X squared plus y squared plus z squared. So you use the distance formula, and then you square it. So now we want to integrate around that region. So I'm going to draw in some axes here just so we can write up that region. Right, so down here is the region when you project this down, right? So you get that region like that. And so that's something you may want to draw again in 2D. So that's a circle that you're integrating around in 2D, like that. You can move that right about there, it's probably fine. So now you have that as a circle. So you're setting the z equal to the square root equal to 2. Right, so we want to know what that projection is down to the level curve, basically, when z is equal to 2. So this would be 2, negative 2. So the lower half is going to be, well, write down the function first. It's x squared plus y squared equal to 4. So the lower half is negative the square root of 4 minus x squared. And then the top is positive square root of 4 minus x squared. And so you're going to integrate around this thing. So we can put in a representative rectangle again, like this. So you're going to be y equals the lower to y equals the upper, which is the root, from negative 2 to 2. And then you go from, or first you go from the lower function to the upper function in the 3D case up here. So z equals the lower, root x squared plus y squared, to the upper, which is z equals 2. So your mass, come way over here, is equal to the integral. So try to set this up now. Go ahead and stop that and set up what do you get. So the inner is the k, the delta is k times x squared plus y squared plus z squared. And that'll be dv, but your first function is the lower, which is the z, so it's dz. So it's from the square root x squared plus y squared to 2. That's z equals. Now you're down to the lower function, which is y, to the upper function, right? So then you get negative the square root, and I'm going to move this to give myself some more room. You got to squeeze all this stuff in here. So lower function is negative root 4 minus x squared to the upper root positive 4 minus x squared. And then you're adding that up from negative 2 to 2. Negative 2 to 2. And that would be your mass. Let me move this out of here because it's kind of in the way. I'll just put it here. So that's what your mass would be. Now that actual integral would be quite interesting to do. Maybe not too bad. One you get, well, no, let's see. Oh, almost forgot. This is then dy, because it's y equals to dx. Remember, your outside is the x equals negative 2 to the x equals 2 as you go across. And you can put them down in the limits if you want to remember the order. And that order will change. A little later, we're going to go different directions. We're going to go side to side first, and it'll change up a bit. The next section is 15.7, which is on triple integrals in cylindrical and spherical. So what we're going to define is what is called cylindrical coordinates and spherical coordinates. It's a whole different coordinate system that we'll talk about. Let's go ahead and do another video for that.